see the whole screen. So let's get started. So I like to start my presentations by kind of discussing conceptually what soil is. When we think of soil, we usually think of a solid material. But in reality, soil is actually a combination of solids, certainly, but also water and gas. And you need all three of those things together in order to make healthy soil for healthy trees. And if we were to look at the actual pie chart of soil composition, it's a little surprising that only about 50% of healthy soil, and I do put emphasis on healthy, certainly there's plenty of non-healthy soil out there that won't
listen to this while I eat. I'm
stream dispersion. 50% solid,
okay.
about 25% gas, and about 25% water by volume. So that means that about half of the soil consists of non-solids, basically air, and soil water. This is very important when you think about it because obviously plants need oxygen and they need water to get down to their roots. If we were to break it down even a little bit further, our solid material, about 5% of our soil consists of organic matter. That means the other 45% is our mineral matter, and then 25% gas, 25% water. Let's talk about those solids a little bit more. Even though they may not consist or may not make up as much of the soil as we may have originally thought, they are still very important. And they really, when we're describing soils, we're really describing differences in the soil solids. When we're saying, oh, it's a clay soil, it's a very sandy soil, what we're doing is making a remark about the soil solids and the types of solids that are in that soil. So again, the mineral fraction consists of 45% of the volume of the soil. What is the mineral fraction? Very generally, it's the percentage of sand, silt, and clay in your soil. Certain soils are naturally sandy, certain soils are naturally silty, certain soils are naturally clay, and then there's many other soils that are a combo of all three. In Arlington and Alexandria, we'll always find some sort of combination. It's extremely rare anywhere in the world to find 100% pure sand. The closest thing you'll find to pure sand is if you go to Rehoboth Beach or Ocean City. But around here, you're not going to find that. You're always going to have some sort of mixture of sand, silt, and clay together in our local soils. And then our organic fraction, 5% of the soil, consists of both the living organisms, so everything alive in the soil from the plant roots to burrowing critters like worms down to tiny microscopic bacteria, are all actually considered to be part of the soil. And then there's the dead organisms, the decomposing organic matter, which is also part of that 5% organic fraction. So looking a little deeper at the mineral fraction, what constitutes sand versus silt versus clay? The definition of sand, silt, and clay is actually not one based upon the minerals that you find, but the size of the particle. So this is the U.S. Department of Agriculture's definition, but they define sand as any particle in the soil, mineral particle in the soil between 2 and 0.05 millimeters in diameter. So pretty small, but much bigger than silt, much bigger than clay. Silt is any mineral particle between 0.05 and 0.002 millimeters, and then clay is any mineral particle less than 0.002 millimeters. What does that really mean? Obviously, 2 millimeters is small, but you can see that with the naked eye. A millimeter you can see with the naked eye. Once you get down to 0.05 millimeters, you're really beginning to verge into microscopic territory. Silt and clay are all microscopic. Clay, 0.002 millimeters. We can kind of tell by that number, it's a bit of an awkward measurement. Obviously, it's very, very small. But to put it in maybe a little bit more understandable terms, 0.002 millimeters is the same as saying 2 microns. 2 microns are 2 millionths of a meter. So a meter is about 3.2 or so feet wide. So imagine about a 3.2 thereabouts wide meter. And somehow you have this tiny little knife that can slice that meter into 1 million equal slices. If you put 2 of those slices together, 2 millionths of that meter, that is the diameter of the largest particle of clay, and they can get a lot smaller than that. This picture does a pretty good job of showing the relative sizes of sand, silt, and clay. But I also heard a presentation years ago from a master gardener in Arlington who I think put it really well. If you've ever gone to, I can't say a Redskins game anymore, the Washington football team game, the stadium would be akin to the size of a particle of sand. Your car would be like a particle of silt, and the parking ticket on your windshield would be like a particle of clay. And that gives you somewhat the relation in sizes between sand, silt, and clay. So even though they all seem very small to us, clay is immensely smaller than silt, and silt is immensely smaller than sand. Sand, silt, and clay are important because they determine what's called the soil's texture. Texture is a good term for what this is. Texture kind of defines how the soil feels. Is it smooth? Is it sticky? Is it gritty and loose? And texture is very simply the percentage of sand, silt, and clay. So we take a percent sand, percent silt, and percent clay and add them up to 100%. That is your soil's texture. Texture has a lot of effects on the behavior of the soil. A really sandy soil will be very porous. It'll allow in a lot of air and water, but it won't hold on to it. It'll allow that material to leach through very, very quickly. On the other hand, a very clayey soil holds a lot of water, but it tends to be very hard and gummy and sticky and hard to work, and sometimes get waterlogged because it holds so much water. So the texture does have a lot of important effects on the behavior and fertility of the soil as well too. The organic fraction is the other portion of the soil solids, and again, that's 5% of the soil by volume. It consists of the living material, so anything alive in the soil, from stuff that we really don't think of as soil, like our groundhogs, we actually, from a scientific perspective, consider that to be part of the soil. Foxes, down to more familiar soil organisms like your earthworm, even smaller things like still multicellular and, for the most part, macroscopic insects like springtails, mites, fleas, and things like that, down to the really small stuff, both soil bacteria and soil fungi. Now, fungi is interesting. It can be macroscopic, of course, if you've ever seen a mushroom or fungus grow on a dead tree log, but most soil fungi is microscopic. And actually, when it comes down to actual weight of material, these small things, the bacteria and the fungi, make up the vast majority of soil living organic material. So it's estimated that every teaspoon of healthy topsoil has anywhere from 100 million to 4 billion bacteria residing within it. So if you pick up a handful of soil, you're almost certainly holding more living organisms in your hands than there are people on Earth. For fungi, the microscopic fungi take the form of these little tiny root hairs called hyphae. They look like little fine white threads working their way through the soil. You can't see them, of course, unless you're using a very powerful microscope. But if somehow we could take a teaspoon of the healthy topsoil and with a tiny little pair of tweezers extract all of those soil hyphae, soil root hairs, and lay them end to end to end, we would find that they'd stretch anywhere from about 40 yards to 40 miles of root hairs per teaspoon. So there's really a tremendous amount of stuff living in soil, but most of it's invisible to us because it's the microscopic bacteria and fungi. That's the living material, and of course the dead material is the other portion of the soil organic fraction, and that is the decomposing stuff that is in the state of breaking down and eventually will turn into soil humus. Soil humus is sort of the end product of decomposition of formerly living organic material. And soil humus is actually pretty resistant. It's sort of the tough stuff that's left behind after all the easy to digest stuff has been burnt up by bacteria, fungi, and other decomposers. So things like sugars and starches and some fats that get decomposed very quickly. What's left behind in the soil humus are sort of the lignin and the cell walls and the fibrous, tough to decompose stuff. And that nice, fairly tough humus can actually stay in the soil 50, 100, 150 years in some cases, slowly breaking down that whole time. But it's tougher than we think it is. So that's soil solids, the mineral fraction and the organic fraction. Of course, the other half of soil consists of air and water. And it's not necessarily analogous to our surface air and our surface atmosphere. It's quite a bit different when you get into soil. And one of the big things about it is it's very heterogeneous, meaning there's a lot of spatial variation from spot to spot. Let's say you have one little soil pore that is kind of closed on both ends, so it's not open to replenishment. That soil pocket of air will turn very high in carbon dioxide very quickly, especially if there's some good organic matter to be broken down and some available living microbes like bacteria or fungi to break it down. They'll break it down, they'll gas off carbon dioxide as their byproduct, and that little soil, closed soil pore will fill up with carbon dioxide and have a lot less oxygen than the rest of the soil and from our air on the atmosphere. In addition, with the water, you can find little pockets of acid water, little pockets of more basic water, some pockets of neutral water. It all just depends on what kind of microbial activities are occurring in that little section of soil. The microbes and the biological activity creates a lot of heterogeneity in the quality of the air and water pockets throughout the soil. But generally speaking, in general trend, the atmosphere of the soil air generally tends to be significantly lower in the oxygen content than the air that we're breathing up here on the surface. So the reason that this is all important is that in a nice, healthy, natural soil, division of air, water, and solids is such that they really give the plants what they need. So you do need a lot of solid material in your soil just for basic physical support. If we had a significantly smaller portion of solids in our soil, maybe 25% or 30%, every time we had a windstorm, we'd see thousands and thousands of trees getting knocked over. They obviously need a solid base to set their roots in so that they can stay upright during wind, during rain, during snow, anything that's weighing them down or pushing them from side to side. They need enough water and air, specifically oxygen in the air, to keep the roots healthy, to keep the plant hydrated, and to free up adequate nutrients. So soil only takes up two things through its roots: water and oxygen. Now you say, well, what about all those nutrients? It does take up nutrients, but those nutrients have to be dissolved in water for the plant roots to take them up. So you want water getting down into the soil, dissolving some of the available nutrients that are there so that they then turn into a form that can be taken up by the plants. Solid nutrient is great, but it's not going to be taken up by the plant until it dissolves. And you also want enough water and air to keep the microbes happy and active as well too. There are microbes that can live in oxygen-free environments, but generally speaking, there's a lot more that like to live in nice oxygenated, moist environments. So they want a little bit of water to keep them nice and moist, but they don't want so much water that it pushes all the oxygen out of the soil. If you have a moist soil with a lot of available oxygen, you're going to have a very happy population of bacteria and fungi, and a happy population of bacteria and fungi will be a very effective population of breaking down organic matter and recycling the nutrients that are within there, and releasing those nutrients out into the soil where the plants have a shot at taking them up. So how does your soil attain this nice balance of 50% solids, 25% water, 25% gas? Well, it's through something called the soil structure. So this is the other very important physical characteristic of soil that helps determine its fertility. Soil texture is the first one that we briefly talked about. Soil structure is the other one. Soil texture is the percentage of sand, silt, and clay in a soil. Soil structure defines how those soil solids, sand, silt, and clay, and organic matter are arranged, or how they clump together. It doesn't sound like that would be that important, but it really is. When you're looking at a soil, again, it looks solid from a distance, but if you actually look at it up close, you'll see it consists of these discrete little clumps of solid material. We call these clumps PEDs. So the official term for the study of soil is pedology, the study of PEDs. So a PED is just a discrete small clump or aggregate of soil. In a way, looking at a big excavation of soil is kind of like looking at a bowl of cereal. From a distance, again, you look at that bowl from across the kitchen, it may look solid, but when you get up close, you'll see that bowl consists of individual flakes, individual O's, individual puffs, whatever soil you happen to be eating that day. Soil is kind of the same way. It's made of these individual little clumps, and you can kind of see the basic shapes of them here. So we've got granular structure. This is a very common type of PED, type of clump that we find up in our topsoil. We've got blocky structure, which shape-wise is basically the same as granular structure. It's just bigger. Each individual PED is bigger. And you'll find that as you dig a little bit deeper into the subsoil and start encountering some of those more clay-rich layers below, you'll find that blocky structure. And sometimes you'll find these other structures as well too. Both single grain and massive are basically what you get when there is no structure. A massive structure might form in a really clay soil that has no structure. It's basically just one huge blob. The whole soil is just one big solid brick. Single grain is when the structure doesn't really come together at all. Everything is just an individual diffuse grain of sand, silt, and clay. There's no clumping whatsoever. And then there's platy structure, and that's something that we often find in urban soils. So granular structure, again, is very common up in the topsoil. Blocky structure is very common down in the subsoils. And unfortunately, platy structure, and to a lesser extent, massive structure and single grain structure is common in urban areas. Platy structure often forms when you take your nicely aggregated granular soil or blocky structure and you run over that soil with a heavy weight and compact it, pack it down. What happens to those blocks and those granules? They tend to get squished into flatter, denser shapes, and that's basically what platy structure is. It's probably a formerly nice, loose, granular or blocky soil that got compacted. Sometimes that happens naturally. Sometimes that happens artificially, as in urban areas with construction, foot traffic, any heavy weight running on top of it. How does soil structure come about? How does it get created? Well, you need both binding and burrowing agents. Binding agents are the things that cause aggregation. You need natural sticky glues, for lack of a better term, to get the soil to clump together in the first place. Some of these natural binding agents are clay and organic matter. Both humus and clay are fairly sticky. They tend to get things adhered onto their surfaces. Microbial decomposition is a very good binding agent. As microbes, bacteria, and fungi break down organic matter, they kind of create these sticky byproducts called mucilages, which is a pretty good term because it's kind of mucus-like in terms of its consistency. And these microbial decomposition byproducts are also good at coating other soil particles and getting them stick together. And then you have really fine root hairs, sort of the fine feeder roots that come off of your larger plant roots and tree roots, act like twine. And they do a very good job of kind of combining small, individual, very almost microscopic soil beds and tying them together into something a little bit larger, kind of tie them together just like twine would. If all we had were binding agents, though, every soil would be massive. Everything would just be one big solid brick of soil. So you also need burrowing agents to create the pore spaces that separate one bed from its neighboring bed. So what are some of these burrowing agents? Well, of course, worms is probably the one that comes originally to mind, and they are excellent burrowers, excellent diggers. The plant roots themselves are burrowing agents. They wouldn't be so great if the root just kept growing and growing and growing and never died, but roots are constantly sending out new growth, and some of that growth dies. And when it dies, the dead plant root decomposes, and what's left behind is an open burrow. There are plenty of other burrowing organisms. Some are bigger, like the foxes and groundhogs I showed earlier. Some are smaller, like insects, beetles. Cicadas are a very good example as well, too. And then there's the purely physical processes. Wetting and drying. Soil wets, it generally expands a little bit. As it dries, it shrinks. And over many cycles of that wetting and drying and changes in volume, you can get some pretty good soil pores formed. Shrinking and swelling does the same thing. Certain clay types, when they get a little bit wet, they swell to much larger than their original size. And then when they dry up, they shrink back down as well too. And then again, that's just sort of a wetting drying cycle on steroids. And then there's freeze thaw, which is the same thing. When soils freeze, the water in them freezes and it expands, causes the soil to get a little bit larger. It kind of creates these ice wedges throughout the soil. When it thaws, the ice turns back into water, and those ice wedges are left as pore spaces. So all these processes together, all these burrowing processes over time, help to break up the soil and create those individual heads. And, you know, the real reason that soil, go back a spot, the real reason that that soil structure is so important is because if you have a well-structured soil, it's a light, loose soil. Well-structured means that basically you have solid, nice, firmly held together beds that won't disintegrate in a heavy rainstorm. And you have nice big pore spaces between one bed and its surrounding neighbors. And those pore spaces then act as sort of the highways that allow oxygen, air, oxygen, and water to percolate from the surface down into the rooting zone. So if you had bad structure, you usually have a soil that doesn't have those great beds and great pore spaces, and it's a lot harder for oxygen and water to get down from the surface to the roots. When we're looking at a final soil, a soil out in the field that's well developed, that's been sitting and weathering in place for hundreds or thousands of years, you're looking at the final process, the final product, excuse me, of the 5 soil forming processes. And they have a terrible acronym to describe these processes. It's CLORPT, C-L-O-R-P-T. It's kind of like the sound of a rock being thrown into a pond. But I think in a way, because it's such a bad acronym, it makes it memorable. So maybe that makes it a good acronym, because if you can remember CLORPT, you can remember the 5 soil forming factors. What are these factors? Well, the CL in CLORPT stands for climate, which is basically a measure of the average temperature and precipitation and its ranges for an area. O is organisms. R is relief. P is parent material. And then lastly, T is time. Oops, excuse me. I'll go through each of those one by one to show you how they affect soil formation. So climate, temperature, and precipitation. Basically, the rule is for soil formation, the hotter the temperature is and the more moisture you have in your climate, the quicker things break down. So a hot, moist climate tends to create an environment where weathering is very fast, both weathering of organic material and weathering of mineral material like bedrock. So generally speaking, hot, wet climates tend to have very weathered soil, very deep soil, not necessarily very fertile soil though, because as water passes through the soil, as rain, as snow, as any form of precipitation, it tends to leach things out. As you build up a lot of acids in the soil, materials tend to break down faster, and bases that are important for soil growth, like calcium and magnesium, tend to wash out of the soil. On the corollary, if you have a really cold soil, that is often a soil that contains a lot of organic matter, because as that organic matter drops to the ground as leaves, as dead animals, as manures, it tends to stay in the soil for a long time, because really, really cold soils generally do not cause things to break down quickly. Breakdown is much slower, so stuff remains in the soil for a significantly longer period of time. We've got organisms. Organisms are generally responsible for the breakdown of organic material in the soil, and especially when you're talking about trees, they're responsible for inputting organic material in the soil. What is one of our big inputs of organics into our local soils? That would be leaf fall during autumn. When those leaves fall, they land on the soil surface, but they don't stay there forever. They start to decompose, and that's the result of those little organisms that are living in the soil. The larger soil organisms, your worms, your beetles, begin to shred up and break down those big pieces of leaf and other decomposing organic material. And once they're broken down to a nice size, then the small stuff, the bacteria and the fungi, really get to work on it and break it down at a molecular level, decompose it, get energy from it, and also release a lot of the nutrients that are tied up within the bodies of that leaf fall and other dead decomposing organisms. So they break down organics, and the reason that's really important is that helps to cycle nutrients through the soil. It gets nutrients that were locked up in that leaf, locked up in that manure, locked up in that dead animal, and they put it into a form that can be dissolved in the water and then taken up again by plant roots. So they're great nutrient cyclers. Relief, just another term for your landscape position, is responsible for the erosion and deposition that you see throughout soils. If you have a soil that's on a very steep slope, generally that's going to be a fairly thin soil, meaning you don't have to dig down very deep until you hit bedrock. You might find it's a very stony soil too. Maybe there's not a lot of clay or other fine minerals in there. Rather, there's a lot of sands, gravels, and rocks. Why is that? Well, on a really steep slope, every time it rains, water's going to go rushing over the surface of that slope at a fairly quick pace. And the faster the water flows across the surface, the more power it has to erode those fine, small particles and wash them away. So a soil that forms on a really steep slope just never really gets the chance to weather in deeply. It's a naturally eroding landscape, and therefore, as the soil forms, a lot of it just washes away. Where does it wash? Down to the bottom of the hill. Water's very predictable. It only goes in one direction, and that's downhill. What's down at the bottom of our hill? Our stream valleys, our floodplains. Those soils tend to be areas of natural deposition. In a floodplain, every time it floods, water spills out over the floodplain surface, slows down. As it slows down, the sand, silt, and clay and other materials that were entrained in that water deposit on the surface, and you get a few, maybe even an inch or two of new soil every time you have a major flood. You can see this in action if you've ever walked along the walking trails in Riverbend Park or Great Falls Park that are very close to the surface of the Potomac. Riverbend Park is a really good example. Every time we have really heavy rain and then the waters recede and things dry out, if you walk across the pathway there that's right next to the banks of the Potomac, it almost looks like somebody from the park came in and repaved it with some nice new loose sand. But it wasn't anybody from the park, it's just the river itself depositing another ½ inch or so of sand that it was pushing along from the Blue Ridge. Parent material is also very important too. So we get traits from our parents, eye color, height, weight, things like that. Soil gets traits from its parent material, from the rocks and sediment from which it weathered. So a lot of the chemical and physical traits you find in soil can be closely tied back to the parent material. For instance, we've got some soils on the western side of Fairfax County that formed from a type of rock called diabase, which is an igneous rock. And this rock has a lot of naturally it has a lot of bases in it, a lot of calcium, a lot of magnesium. So the soils that form from it tend to be a little bit more basic and very rich in calcium and magnesium. Those soils can be 20 feet away from a soil that formed from sandstone and siltstone and shale, which is the other common rock type out in western Fairfax. So maybe you have one diabase soil, you walk 20 feet, and then you're on a soil that formed from siltstone. That new soil from siltstone tends to be very red because it has a lot of iron oxide in the siltstone, and that iron oxide then shows up in the soil as well too. It tends to be a lot more acidic than the soil that formed on the diabase. And it tends to have a lot less clay as well too. And I'm not sure why, but when diabase breaks down into soil, it creates a really, really sticky clay soil. When siltstone breaks down into soil, as you might imagine from the name, it creates a really silty soil. So the parent material can have some pretty intense effects on the final appearance and traits of the soil. And then lastly, there's time, which is a master variable. This is a very general statement, but it's estimated that it takes anywhere from about 100 to 500 years to create every inch of soil. So it takes a long time for climate and organisms and relief and parent material to transform unweathered bedrock, unweathered sediment into the nice clay layered soils that we see out in the field today. Some people hear that last statement, 100 to 500 years to create an inch of soil, and they despair a little bit. Does that mean you need 7,000 years to improve the soil in your backyard? No. You would need 7,000 years if you wanted to create 8-9 inches of new soil. But that's not what you're trying to do. What you're really trying to do when you manage your soil is take the soil that you have and make it more fertile and richer. And that can be done in a growing season or two. So building new soil, depths of new soil takes time. Enriching the soil you have goes much, much quicker. So after climate, organisms, relief, parent material, time have those hundreds and thousands of years to beat down on that unweathered bedrock and sediment, what is the final result? What does our finished soil, our well-weathered soil look like? Well, it's like a layer cake. It consists of layers which we call horizons. Your A horizon is up at the top, and this is what we commonly refer to as topsoil. It's our first layer below the surface, and it's very rich in organic matter. You can almost always tell where the A horizon is based on its color. It's going to have this nice dark brown or black color. I like this picture because it shows the layers pretty well, but this is not a local soil. I'm pretty sure this is from upstate New York, but the reason I chose it is because it shows the layers really well. However, it can throw you off a little bit. If you think your soil is going to look like this soil, you unfortunately are mistaken. In Virginia, we're lucky to get 3 or 4 inches of A horizon. That's just the sort of soil that we get around here. So this nice thick topsoil that you're seeing in this picture, don't aim for that in your own yard. It's pretty much impossible to get around here. If you get 3 or 4, or even better, 5 inches of nice healthy topsoil, you're doing very, very well. Below our A horizon, we can sometimes, I would say less than 50% of the time, but sometimes find an E horizon. E stands for exit. It's the layer that everything is leached or washed out of. Up in the A horizon, you have a lot of organic matter decomposition. That's where we have the most humus. That's where we have the most microbial activity, because that's where the most organic matter is. So all the microbes and biological activity is kind of packed into the A horizon. Not all of it, but the most intense biological activity is occurring in the A horizon. As organic matter breaks down, it creates natural acids. As water passes through the soil after rainstorms and snow melt, it washes those acids through the soil, and the E horizon is sort of the layer that takes the brunt of that. So it looks kind of pale and gray, and that's because those natural acids have washed through and leached or stripped away all the material that could give a soil color. These are things like clay. Clay generally tends to make the soil red, orange, or yellow, and things like organic material, which tends to make the soil dark brown or black. All that stuff gets stripped out via acid weathering, and what's left behind is this sort of pale, gray, almost white color layer. Again, in Virginia, sometimes we will have E horizons, but if we do, they're generally about the same width as the A horizon, which would mean anywhere from about 1 to 4 inches. So they're not very big, but sometimes you can find them. What we do have a lot of in Virginia, and is actually thicker than what is shown here, is our B horizon. This is where you hit what is colloquially termed red Virginia clay. So if you're digging through your soil now when it's been really dry and really hot for a couple weeks, if you hit this red Virginia clay layer, it's going to feel like you're digging in a brick. It's going to be pretty hard and pretty dense feeling. And actually that makes sense because they do make bricks out of this material. But our B horizon is basically where our clay gets stuck. So clay actually starts forming up in the A and the E horizons, but over time as water, snow melt washes through the soil and passes through the soil pores down into the deeper subsoil, it picks up a lot of those small clay particles on its way and washes them down into the B horizon. So it's interesting, over time the B horizon actually gets thicker and thicker and thicker as more and more clay gets washed down into the soil and deeper into the soil. So oftentimes you can tell how old the soil is based upon the thickness of its B horizon. But that's a little bit of extra detail. For us, the B horizon is the layer that is generally highest in clay content and usually also the most colorful. So when you see your reds and your yellows and your oranges and they're really popping out, chances are you're in the B horizon. Below that is the C horizon. This is sort of a border layer between the highly weathered A, E, and B horizons above and the unweathered to just slightly weathered bedrock or sediment down below. The C horizon can take a lot of different forms, but generally speaking, you can guess as to when you're in the C horizon by how much clay there is. Usually when you get to the C horizon, you'll start to see the clay content reduce. The soil will start to feel a little bit looser, oftentimes a little bit grittier. You might see more large particles like sands, gravels, boulders, rocks in the C horizon. And it'll often feel looser and drier than the B horizon above it because that clay content is dropping and there's just not that clay there to hold on to water and moisture. So if you're getting kind of a drier, dustier, looser, more powdery feeling soil underneath your B horizon, especially if you see a lot of gravels and rocks, chances are you're in the C horizon. It's the border layer between the highly weathered soil layers above and the just barely or unweathered rock and sediment down below. And some of you, if you dig down deep enough, will hit the R horizon, which is your solid bedrock. For those of you who live in North Arlington, you have a chance at hitting solid bedrock. It's still probably deeper than you'll ever dig because oftentimes it's 5 to 10 feet deep, sometimes more. If you live down in southern Arlington, especially southeastern Arlington or in the city of Alexandria, chances are you will not see bedrock no matter how deep you dig because those soils are on the other side of the fall line. They're in the coastal plain, and coastal plain soils were formed from bands of sediment that washed in from either the old Atlantic Ocean or the old Potomac River. So in some cases, like if you go down to Old Town Alexandria, you probably have to dig down about 200, 300, maybe even 500 feet in order to hit solid bedrock, because it's just covered up by all these bands of sediment that washed in many thousands of years ago from the ancestral Potomac or even the Atlantic Ocean. So a healthy soil plant system, what it's going to look like? Well, the A horizon is really the most important layer when it comes to plant health, because that's where so much of the organic matter and the decomposition of the organic matter, and thus the freeing of soil minerals and nutrients occurs. So you want to have an A horizon that has lots of organic matter and a very nice, loose, granular soil structure. This allows for lots of microbes to thrive. The more microbes you have, the more breakdown you're going to have of that organic matter. As the organic matter breaks down through microbial decomposition, it releases mineral nutrients out into the soil, and some of it can be dissolved in the water, and that material that gets dissolved can then be taken back up by the plants. You also want that nice granular structure, because a loose, granular structured soil will allow a lot of oxygen and water down into the soil, which is really great for these microbes. They love a moist, oxygenated environment. If they have that, they have plenty of oxygen, plenty of water, they're going to be more active, and the more activity they have, the more breakdown you're going to get of your organics and the release of nutrients. So this is what your structure should look like generally. We call that, some people call it crumb structure, because it looks like little crumbs. And oftentimes you can see this if you go out into your lawn and you brush aside the blades of grass and you look down on the soil surface. You can see these little visible clods. That's a good sign. If, on the other hand, the soil looks like sort of a flat sheet and you don't see any visible individual aggregates, that's oftentimes a sign of a soil that's been a little bit compacted, a little bit crusted over. So the water, as it passes down into the soil, the good crumb structure allows in plenty of oxygen and water, and as that water passes into the soil, it dissolves the nutrients, and the dissolved nutrients can then be taken up by your plants. So an A horizon with lots of organic matter to break down and release its nutrients, and good granular structure, which allows in water and oxygen, which powers the organisms and allows them to break down that organic matter, is what you really want in your A horizon. How do you get it? Well, got to feed it, got to add a lot of organics. And it's a virtuous cycle, because a well-fed plant will grow more. And as it grows more, it's going to drop more leaves, send out more exudates from its roots. So it basically feeds the soil that feeds it. So if you get good plant growth, that good plant growth will add more organic matter to the soil. That organic matter will then feed the microbes that are living in there. They'll be more efficient at breaking down organic matter and recycling nutrients, and the cycle just strengthens itself. Moving down a little bit for a healthy soil and plant system, when you get into your B horizon, actually, people complain about clay. Clay can be very useful because clay retains a lot of water for uptake by deeper plant roots. So most of your plant roots, even your largest tree, will have 90% of its plant roots within the top foot of soil. So the plant roots that get down into the B horizon are oftentimes those deeper roots, but those deeper roots are very important because they can tap into a good bit of water that's stored down deeper, which would be very important at a time like now when the soil is going to be fairly dry and dusty. So those deeper, not exactly tap roots, but deeper roots can get down in that B horizon and suck up some of that water that's being held by the clay down there. And of course, it's not as much as what happens in the A horizon, but there still is microbial breakdown of organic matter, and thus the release of nutrients occurring in the B horizon. It's a small fraction of what happens in the A horizon, but it's not insignificant. We also find that a lot of soluble materials that may have leached out of the topsoil will filter out down here. They'll be strained out in the B horizon. What are some soluble materials that are pretty important? Well, things like a lot of the nitrogen compounds are actually fairly easy to dissolve and fairly easy to wash down deeper in the soil. So we have a nice clay B horizon. There's a good chance that that clay will catch that soluble nitrate or other nitrogen containing material before it washes out of the soil. And then below that you have your C horizon, which is generally, again, more sandy and gritty than your B horizon, much less clay. But it still provides water retention. Still a significant amount of water can be held in the C horizon, even though it doesn't have the clay content of the B horizon. And this water will be accessible by some of the deepest plant roots. and it still continues to filter out both soluble and I should say solid material as well too. So it kind of prevents the groundwater from getting polluted. And the water that passes through the sea horizon does eventually make its way to the groundwater, so this helps with groundwater recharge. Now, in urban areas, we see a lot of changes occur with the soil. Almost all of them are bad when it comes to the health of the soil and the plants that are growing with it, unfortunately. One of the big ones is compaction. So let's say we have this nice, loose, well-structured soil. It's got big pore spaces, nicely held together soil pores. It can easily pass water and air down from the surface to the rooting zone. Well, what happens if we run that soil over with a bobcat, with a bulldozer, with a grader? What happens if we just have, say, hundreds or thousands of school kids running across it? Well, that soil gets compacted. It becomes a lot more dense. During the development process, like the picture shown here, not only packing the soil down, but the weight of this machinery tends to tear up the soil pores, disintegrate them, pulverize them as well too. So, the soil beds. So the aggregates may not even exist at this point. What happens during compaction? Well, you move from a fairly healthy soil, which has 25% air, 25% water, and 50% solids by volume, and you get a significant loss in pore space. So now you have a soil that is a much higher percentage solids and a much lower percentage of pore space, which means there's a lot less area for gas and water to fill up. So even after a heavy rain, a compacted urban soil cannot hold nearly the volume of water that a healthy soil could. This compaction reduces the ability of air and water even to infiltrate into the soil. So there's less storage space within the soil, and there's less chance for the water even to get into that storage space in the first place. So I call compacted soil impervious light. If you're not familiar with an impervious surface, it's any surface that lets no water pass through. So this would be things like the rooftops of buildings and paving, concrete, asphalt, and the like. Compacted soil lets a little bit of water pass through, but not nearly as much as what would have been held in a nice, natural, loose soil. So therefore, I think the term impervious light kind of applies fairly well to it. Here's your well-structured soil. Nice, loose beds with big pore spaces in between those beds. What happens when it rains? Most of the water just percolates right down through those pore spaces. Here's that same soil after it's been compacted into a platy structure. What happens when it rains? Some water gets in, a lot of the water stays up there at the surface. Doesn't have a chance to get in. And we'll see the sort of the macro effects of both impervious surfaces, all of our paved surfaces and rooftops, and compacted soil combined when you look at a highly urbanized landscape. A high proportion, sometimes the majority of water that falls on it becomes surface runoff. And here it's showing that precipitation is coming down, 15% infiltrates, 30% evaporates and transpirates back to the atmosphere, which leaves 55% to become urban runoff. This is at a highly urbanized landscape. That same landscape before it was developed, water falls down, 50% of it infiltrates into the soil, 40% evaporates or transpirates. What's left, only 10% becomes runoff. So we've got a 550% increase of runoff from 10% to 55% as we move from a very natural environment to a very urbanized environment with the concomitant impervious areas and compacted soil. The other issue with compaction is it tends to create a very dense, strong soil. So this is a fairly typical scene from a newer suburban development, tract housing development. You see the houses get built, the roads get laid down, and then sort of the finishing touch is the developer comes in, either puts grass seed or sod down, and then plops these new decorative street trees along the roadways. Now, if you come back to this development in 20 or 30 years, that tree should be pretty big by that point. It's sitting out there in the sun. It's got no real competition. Hopefully somebody's watering it. It's got a chance to grow really fast. But a lot of times when you look at these, you come back in 20 years and that tree doesn't really seem to have grown much at all. I think one of the reasons for that is that it's surrounded by very dense urban soil, which is, again, strong, and it's very difficult for roots to get the strength to even penetrate that soil. So in a way, the little hole that the developer dug out so we could probably put this burlapped root mass in may be, in effect, be the confines of the roots. That's sort of the prison that the roots are trapped in, because it may not have enough strength to send its roots out into the compacted soil that's underneath that sod or turf grass around it. And if the roots can't grow, the rest of the tree is not going to grow either. We're beginning to see this. This is a really good illustration. You may not recognize the street, but this is Pennsylvania Avenue, the sidewalk on Pennsylvania Avenue between the White House and the Capitol. I think these are all pin oaks. They're oaks of some sort. I'm not an expert on IDing trees, but you can see the difference. It's same oaks, same age. Look at the difference in the growth between the oaks that are on the street side and the oaks that are on the far side, away from the streets and closer to the building. I wouldn't say these oaks are growing in good soil, but they do have access to quite a bit of open soil there. You can see this probably 20, 30 foot wide swath of grassed area between the sidewalk and the building behind it. These oaks, on the other hand, same type, same age, are grown in little tree boxes in the sidewalk. And that means that their roots only really have access to the soil within that tree box. And what's surrounding that soil is the sidewalk, and underneath that sidewalk is highly compacted soil. And then, of course, there's Pennsylvania Avenue on the other side. What's underneath that? Even more highly compacted soil. And the roots won't really have the ability to push through the soil on either side. So they're limited to this little tiny slot of available looser soil. And you can see how they've suffered. Their size is much, much less. Their canopy is much smaller than the oaks over on this side, where their roots did have access to at least a small amount of suitable soil. So if the soil is so hard and so dense that the roots can't penetrate it, the trees and other organisms, other plants that are growing there are going to really struggle and probably stay stunted. And we're actually doing a study right now through my office. We're doing contract work for Arlington County, looking at soil in residential areas, both new residences and old residences. We haven't finished it yet, so we don't have all our data, but I was just going through some of our preliminary data today. One of the things we're doing at these residential sites is taking a penetrometer reading. What that basically is this device you see here. It's a spike with a pressure gauge on the top. You push that spike down into the soil, and you read how much pressure it takes, how much pounds per square inch of pressure it takes to push that spiked device down into the soil. Generally speaking, if you're hitting 200 pounds per square inch on your penetrometer, that's about the cutoff for where roots begin to struggle to push through the soil. So you start seeing root limitations at 200 psi, and then at about 300 psi, that's sort of the impenetrable barrier. If your soil is 300 psi or higher, generally speaking, you're going to have very, very, very few roots that can even pass through that. So that almost becomes a complete root barrier. And what we found is that so far, and this is preliminary, we haven't looked at all of our sites yet, but so far, 60% of the readings we have taken with the penetrometer have shown that there is soil with penetration resistance of 300 psi or more within 6 inches of the surface. So 60% of the time when we stick this penetrometer down into the ground, we're reading a reading of 300 psi somewhere within the first 6 inches. So you can tell that soil in Arlington, and certainly Arlington soil is no worse than any other urbanized area, so I would extrapolate and say this holds true for soil in many urbanized places. It's very dense, and that density can really limit root growth.
Oh, Dan?
Yes.
This is Nora. I just wanted to interject that Tree Stewards own one of those machines, and we've used it for education with some homeowners to point out to them how compacted the soil is and how they can change it. So I throw that out there so that other volunteer tree stewards can borrow it anytime they want.
Excellent. It's a good device. It's fairly simple. It has its limitations, but it's good at getting a whole lot of data pretty quickly and kind of visually showing you the compaction. So it's nice that you have one yourself. Thanks, Nora. One of the other urban effects that we see for soil is mixing. So this is what a natural soil looks like. It consists of these layered, discrete horizons. But during the development process, what happens? The land is graded out and all these soil layers tend to be mixed together. Is that a problem? Well, yes, because when the soil is stirred up, a lot of the fungi that's within that soil will die. Because remember, fungi consists of those long, thin root hairs. So if you start taking the bucket of a backhoe or a grader and passing it through the soil and cutting up the soil, it tends to slice through a lot of that fungi and kill it. Bacteria is single-celled, so stirring up the soil isn't necessarily so bad for bacteria, but it does tend to kill off a lot of fungi, and that can be very bad. In addition, the soil gets mixed. So the fertile topsoil, which again, around us, our A-horizon topsoil is usually only about 2 to 4 inches thick, so there's not a whole lot of it. It tends to get spread throughout the entire soil layer, soil column. It's important to have that topsoil concentrated at the top because it's an area of concentrated organic material and biological activity. When it gets spread throughout the soil, basically those nutrients, those microbes, and that organic matter gets dispersed throughout as well too. So you don't have that concentration of biological activity and decomposition like you do in a healthy soil because it's spread all over. And this is sort of the soil that results. It looks much more consistent from top to bottom. So if you dig up a really disturbed soil, oftentimes it's just sort of red from the top to the bottom. And that's a sign that the soil has been extensively mixed together and you don't have that natural layering anymore. When you have a loss of that productive topsoil, when it gets mixed throughout the entire soil column, you get a loss of microbes, especially up at the top where they would do the most for benefiting root health. You have a loss of humus because that humus, again, was once concentrated where the roots had access to it, and now it's spread throughout the soil. And therefore, with less microbes and less humus concentrated at the top, you have a significant loss in nutrient cycling as well, too. You can also get pH changes in urban soil. I'd say this is less severe than the soil mixing and soil compaction, but it does happen, and it can affect your plant types. Sometimes those pH changes are due to very local land uses. So for instance, if you have concrete, especially walkways or roadways, concrete contains a lot of limestone. So the soil around concrete, especially older concrete that's been sort of decomposing over time, leaching its materials into the surrounding soil, that near concrete soil can often have a significant increase in its pH as that limestone from the concrete leaches down into the soil around it. On the other hand, you can use fertilizers that lower the pH. And this is true of those fertilizers that contain ammonium or sulfur, elemental sulfur. Those tend to, over time, push the pH down. It's usually not a real severe reduction, and it can be changed quite easily with a little bit of lime, but it can happen. And if you don't know what's happening, it can harm some of your plants, especially if they're very pH sensitive. Why is pH important? It's not important in and of itself, meaning it's not that you build up too many acids and the acids start eating away at the plant roots. Rather, it's important because it affects the availability of nutrients. Certain nutrients are more available at certain pHs and less available at other pHs. Basically, they're more soluble, more easily dissolved at a certain range in pH. So when a plant likes a certain range in pH, what they're really saying is, I like the nutrients that are available, readily available at that pH range. Not so much I just like acid or basic conditions. I like the nutrients that are available at that acid or basic condition. Generally speaking, there's kind of a sweet spot window between about 5.5 and 6.8. Virtually all the plants that you're trying to grow will grow well within that window, at least all of our local natives. But there are some outliers. If you're trying to grow some of the acid-loving plants, your azaleas or your blueberries or hydrangeas, for example, they generally like a pH that's on the lower side, so maybe 5 or so, 5 to 5.5. So in some cases, you may have to change your soil pH in order to support the plants that you want to grow. But generally speaking, almost everything around here will grow well in that 5.5 to 6.8 pH. And it's pretty easy to tell what your pH is by getting a soils test, which you can pick up in any public library. Salt is a big problem in urban areas. And it's a tough problem because there's an obvious need to keep our roads safe and keep cars from sliding off. But every time we put down salt, there's a high chance that a good amount of that salt is going to wash into our soil, especially if that soil is very close to the roadway. and salts can build up and they can do a lot of damage. Salts can wilt plants. You're probably familiar with that, but one of the things that people aren't so familiar with is a lot of salt will destroy the soil structure too. Salt tends to make soil beds, soil aggregates, break down and disperse. And this tends to clog up the soil pores, and you can create almost a totally impermeable soil if you add too much salt to your soil. And poor soil also leads to poor water quality. So there's two reasons to have healthy soil. Obviously, we want our plants to grow well, but when we have that healthy soil, chances are we're going to have healthy streams and rivers as well too. Why is this? Well, natural soil acts as both a filter and a sponge. It cleans water and it holds water. Specifically, organic matter and clay, so even more than just organic matter, specifically soil, humus and clay, have small electric charges. It sounds kind of strange, but they carry a small electric charge that attract dissolved ions out of water and bind them in the soil. What are some of these ions? Well, most of our soil nutrients exist as ions. An ion is just a charged particle floating in the soil. So nitrate, phosphate, calcium and iron and zinc ions will be attracted out of the water and stick to the surfaces of humus and clay, almost like a magnet attracted to another magnet. This is great because it keeps those essential nutrients within the soil, and it also keeps those essential nutrients and other materials out of our waterways. Water itself is attracted to the surface of clay and organic humus. So much of the water is retained in the soil. This is very important too, because especially on a dry streak like we're having right now, we want a lot of water to stay in that soil so that our plants don't wilt. So as water passes down through the soil filters the water, removes a lot of those charged ions from it, and retains a good portion of that water volume within the soil itself. Very, very important. Keeps the plants hydrated, and any water that does pass through and enter into the groundwater has been filtered and cleaned. And it sounds a little odd, but if you run water through dirt, it actually comes out a lot cleaner on the bottom. So it's one of the best things we can do for our local water quality is pass our rainwater, our stormwater runoff, our snow melt through the soil first so it can be filtered before it flows into the shallow groundwater and recharges our streams and our rivers. So you can in effect think of soil as being like a Brita filter that's spread evenly out throughout the surface of the world. Now the problem in urban areas is density. Urban soil is so dense, plus there's all those impervious surfaces, that we're allowing a lot less water to enter the soil in our urban environment than in our natural environment. What's happening to that extra water? It's becoming stormwater runoff. And in urban areas, we've gone the extra step and created these artificial pathways called our gutters and drains along the side of our roads that takes that excess water, puts it into a pipe underground, and lets it out right at our stream. So we both are creating more stormwater and creating a very efficient, fast path for that stormwater to get down into our streams. What happens as a result is that our streams are eroding from the inside out. They're basically scouring out, scouring wider and scouring deeper every time we have a rainstorm, especially a heavy rainstorm. It's like there's a little flash flood of stormwater that goes rushing at high speed through our stormwater system down into our streams, and it causes the streams to erode wider and deeper. So this is a fairly typical scene, this picture here, of an urban stream. I always point out that that is my coworker, Willie. Willie is about 6'6", so he's a very tall guy. But you can tell his head is about a foot or two below the top of that stream bank, and he's standing on the stream bank, so his feet are about a foot or two above the water height. So that's about a 10-foot stream bank right there. That's not natural. If you see these very sharp, steep, almost cliff-like stream banks, especially if they have bare soil like the one you're seeing right here, and especially if they have tree roots hanging out into the air, you know that that's an area of accelerated, probably human-caused erosion. Now, that doesn't seem like it would be such a huge problem, but we've got thousands and thousands of these little stream channels traversing Arlington, Alexandria, Fairfax Falls Church, Fairfax City. And if every time we have a storm, if even a millimeter of the bank of that stream becomes eroded away, if you multiply that by the thousands of miles of streams we have, that's hundreds and thousands of tons of sediment that are being washed away. Sediment is a pollution, and it's one of the most important pollutants in both the Potomac River and the Chesapeake Bay. And of course, all of our streams in the local area eventually empty into both the Potomac and the Chesapeake. So to recap the effects of urban development, it tends to create a denser soil than was there naturally. This reduces the amount of pore space in the soil, and if you reduce pore space, it reduces the total volume of oxygen and water that's available to the roots and the microbes that live in soil. And you also see a related increase in surface runoff and both erosion on the surface of the land, but also especially within our streamways. Urban development tends to create a strong soil, and it may be so strong that root growth is restricted. The roots just don't have the power to push through that dense soil. And it tends to disperse and degrade topsoil and humus, spreads it throughout the soil column, and kills off a lot of the fungi. It can change the soil pH, both higher or lower, depending on what's being added to the soil. And it can make the soil saltier as well, too. So all in all, urbanization typically degrades the fertility and the ecological functioning of the soil unless we do nothing to correct the damage. So what can we do to correct the damage? Well, we're looking at a new paradigm of plant health, and that is to focus on soil health. So you see a lot of stuff in nurseries labeled as plant food. Well, it's not really plant food. A lot of that stuff's fertilizer, and fertilizer has its place, certainly. But fertilizer in and of itself is not plant food. It's not even soil food. It's more like a soil vitamin. It's not food. It's more the nutrients, nitrogen, phosphorus, potassium, and those things are important, but it doesn't provide energy to the soil organisms. If you're going to feed the soil organisms, you have to add something that contains organic carbon, organic material. Not just the nutrients, but nutrients plus organic material. Now, why do we want to focus on soil health and specifically feeding the microbes and other larger organisms that live in the soil? Well, if you feed the guys that live in the soil, they will do the work for you because they're the ones that power the nutrient cycle. They're the ones that decompose organic material, release soil nutrients, and allow plants to take up those nutrients at a later date. So you're basically adding good food to the stomach of the soil, and the stomach will do its work, digest, and spit out useful nutrients that the plants can use. So how do we kickstart the soil biology and food web, especially in an urban soil that may not be in great shape to begin with? Well, the simple answer is you want to add organic matter. And there's a lot of nuance to this, but that is almost always my recipe, my diagnosis, my advice for improving the health of soil, especially urban soil. Add organic matter. Why? Organic matter is the base of the soil's food web. It's what all those little microbes want to eat. In addition, organic matter promotes soil aggregation and structural development. As organic matter decomposes and becomes basically humus, compost, that humus is one of the great soil glues, the building block of soil structure. So organic matter itself is a food source for organisms. As the organic matter breaks down into soil humus, it also is one of the glues that causes good structural development to form. Organic matter also holds a lot of water and a lot of nutrients, and it's a very light substance, so it tends to decrease the density of your compacted urban soils. Let's look at that water and nutrient holding capacity change to start. So this is a simple graph that shows the relationship of the total amount of water volume that can be held in soil to the soil's texture. And if you remember, texture is the percentage of sand, silt, and clay. So let's say we're starting here at the intersection of the two axes. We're starting with a really sandy soil, 100% sand, 0% clay. And as we move down our axis, we're moving into the loams, which are a nice mix of sand, silt, and clay. And then we keep moving down the x-axis. And eventually we get into our clay. So 100% clay, 0% sand. So we're moving from a very sandy soil and adding stickier, smaller material until we get to a very, very clay soil. What happens to the plant available water within that soil? Well, as you start adding more clay, as you move from your sand to your loam to your clay, as you might expect, more water is able to be stored in that soil. But we're not so concerned about the total volume of water that can be stored in soil. We're concerned with the amount of water that is available to be taken up by the plant roots, what we call the plant available water. And this is the difference between two water volumes, the field capacity and the wilting point. So let's say you had a dry sponge, something that you bought from the supermarket. You buy that dry sponge and take it out of its packaging and you put it under a slowly dripping faucet. What you'll notice is for about 30, 45 seconds, even a minute, the sponge will start soaking up that water. It'll expand, it'll soak up all of the water that falls on it through those little drips from the faucet. And then eventually, after about a minute or so, the sponge is completely full of water, and water starts dripping out of the bottom. So basically, every new drip of water from the faucet passes immediately through the sponge and drips down into the bottom. Basically, the sponge has no more ability to soak up water. At that point, you turn the faucet off. You'll see the sponge will keep dripping for another 10, 15 seconds or so, and then it'll stop. The state that it's in right there, that's basically field capacity. Field capacity occurs like 1 or 2 days after a really heavy soaking rain. During that soaking rain, water is passing into the soil pores are completely full of water, and a good portion of that water just passes right down through the soil. That's analogous to those drips coming out of the bottom of the sponge. But after about a day or so, there's still a lot of water in the soil, but the water is more attracted to the surfaces of clay and organic matter, and it can resist the pull of gravity. So there's no water falling out. So basically, field capacity is the maximum amount of water that soil can hold against the pull of gravity. Now, the wilting point is pretty self-explanatory. That's the volume of water in the soil below which plants will start to wilt. And you'll see that as we go from a sandy to a clayey soil, the field capacity increases. And it's still increasing as we get to 100% clay, but the increase starts to level off, but it's still building higher. However, the wilting point starts to increase too. And here's the problem with clay. It holds a lot of water, but it's greedy. It holds it very, very tightly. So a clay with a lot of water doesn't necessarily have more water that's available to plants, because the plant available water is the volume of water held at field capacity minus the volume of water held at the wilting point. Clay holds that water so tightly that its wilting point is very high. When a plant starts to wilt in a clay soil, there's still a lot of water in there. It's just that water is so tightly bound to the surfaces of the particles of clay that the soil roots don't have the ability to suck it up. They just don't have the suction. Sand holds water very, very loosely. Its wilting point is basically zero. Almost every drop of water in a sandy soil is available to the plant. The problem is there's just not a lot of water available at all because water passes very quickly through sand and sand doesn't hold on to it very well. So where we actually find the most plant available water is in the loams. The loams don't hold the maximum amount. They just hold the most water between field capacity in the wilting point. Now that's great. So that kind of shows you how soil texture is important. But the problem with soil texture is you can't really do much to change it. If you have a sandy soil, you're pretty much stuck with a sandy soil. If you got a clay soil, you're pretty much stuck with a clay soil. Unless you want to do something crazy like bring in 20 dump truck loads of sand to add to your clay soil, you're really not going to be able to change the soil texture. However, what you can do is add organic matter. No matter what soil texture you have to begin with, whether you've got a sandy soil or a loamy soil or a clay soil, adding organic matter will help boost that soil's water holding capacity. So this is what happens when you add, let's say, composted organic matter to your existing soil. No matter what texture you had to begin with, the organic matter greatly increases the field capacity and only slightly increases the wilting point. Organic matter, humus, is a lot like clay in that it holds a lot of water, but it's unlike clay in that it does not hold that water tightly. It allows plants to freely access that water. So it holds a lot, but it holds it loosely. So no matter what your original texture, if you add organic matter, you greatly increase the field capacity, slightly increase the wilting point, and as a result, increase by a good bit that plant available water that's held between field capacity and the wilting point. So that's sort of in a nutshell the effect that organic matter, specifically humus, has on the water holding capacity of soil. How do you add organic matter to your soil? Well, there's a variety of ways to do it. The best is to plant. Plant, plant, plant. The more living roots you have in your soil, the more organic matter you're going to have in your soil. Roots themselves actually kick out a lot of organic matter. Plants are smart. They like to seed the soil with a lot of microbes and bacteria and fungi because they know that those microbes will break down organic matter and supply them with nutrients. So they actually kick out a little nice, easy to decompose organic matter to boost up the number of those microbes around their root zone so that they can get a lot of that benefit in return, those available nutrients. In addition, you know, if you have a plant that it drops its leaves, of course, those leaves will fall down on the surface of the soil, decompose, and become eventually soil humus. So the best way to add organic matter to soil is to have lots of living roots growing in the soil and lots of plant mass growing above the soil, root and shoot mass. But there's other ways to do it as well too. You can leaf cycle. So rather than spending a lot of time and a lot of effort raking up the leaves in the middle of fall, rather you can just take your lawnmower and run them over. Now, if you have a mulching mower, this is very easy to do. You probably only have to make one pass. If you don't have a mulching mower, it's not a problem. All you have to do is probably run those leaves over 2 or 3 times until you've chopped them up into about the size of dimes. And when you've done that, those small dime-sized pieces of chopped up leaves will settle between your grass blades. You probably won't even really see them. So if you live in a neighborhood where your neighbors are a little nosy and very concerned about aesthetics, leaf cycling will not make you the pariah of the neighborhood. It'll still look like a nice clean lawn, but you've got all that good organic rich leaf still in there, and it's going to decompose and become part of the soil and add to the soil's humus. A little more intense, you can do compost top dressing. So if you fertilize your soil, you might want to think, rather than one of your fertilizer applications, maybe you can rake out a thin 1/4 to 1/2 inch blanket of compost over your soil. And again, if it's a 1/4 to 1/2 inch, that compost blanket's going to settle in between the grass blades. It won't be visible from the surface, but it'll be incorporated into the soil naturally as worms start working their way through it, as other burrowing organisms work its way and incorporate into the soil, as rain falls and washes it down into the soil. So what this is showing a lawn that's about to be compost top dressed. The landscapers have come and piled up the compost into discrete little piles, and then you're going to come and rake it in into that nice, even 1/4 to 1/2 inch blanket across the surface. And then I wouldn't necessarily recommend this unless you have a soil that's in really bad shape to begin with. But let's say you have, a really, really dense soil. Let's say you do a project where you have maybe a patio or something that you've taken up and you're going to turn it into a planter. The soil underneath that patio is probably very dense. So if you have a really, really dense, infertile soil, soil that just is not allowing roots to grow freely, you can put a lot of compost or other organic matter on the top, get a rototiller, and just till it on in, mix it all in as deep as you can get it. And then even more extreme, there's something called urban soil rebuilding. And I've got a good video of it. Let's see if this link works. Doesn't seem to be. Let me see. I think I've got it pulled up on my computer here. Here we go. So this is a video of soil profile rebuilding that was taken by Vincent, the forester for Arlington County. And it was done as the title says, George Mason and Lee Highway. Let's see if this works. It's loading. Hopefully it will load. Here we go. Hopefully this will do it. Come on, internet. You can do it. Still loading. Here we go. So what they've done here is they have, this is a tree box, or well, the little grass strip between the sidewalk and the roadway.
We're not seeing it, Dan.
Oh, you're not seeing it?
No, I'm sorry.
Let me see if I can pull it up.
Dan, click
Yes.
on share screen and then click on the video or minimize your PowerPoint.
Ah, I see. New share. Maybe this will do it. Nope.
Yeah, you need to stop sharing the PowerPoint and start sharing the, yeah.
Oh, okay. Whiteboard. Where did it go? Okay. Can you see it now?
Not yet.
No.
Click on the other tab, Dan.
I have. I'm not sure. What are you seeing out of curiosity?
There's two tabs at the top. It says SPR George Mason, has a red dot on it.
Okay.
Right now we're seeing your Zoom login.
All right, let's see. Anything now?
No.
Oh, well. Well, if you go to YouTube, let me just stop the share right there. And I'll try it one more time. How about now?
Yes.
Yes.
Okay. So just to set the scene, I don't think I'll be able to get the sound on this because I'm talking, but this is a little grass strip on George Mason Drive between the sidewalk and the roadway. This is one of Vincent's projects. They're basically trying to make this soil functioning. They're trying to make it a lot more porous. So what they did is they laid out a blanket of compost about 4 inches thick on top of the existing grass. And then they're doing something called urban soil profile rebuilding, which basically requires a backhoe or a digging device such as this. And for lack of a better term, it's basically the scoop and dump method. You lay out a lot of compost on the top, and then you come in one of these large digging devices. You scoop the soil up, you lift it up about 3 or 4 feet, and you open the bucket and you just let it drop back down. And what this does is it creates kind of organic rich channels within the soil, and it really helps to loosen the soil up. And this is a process studied by Virginia Tech, and they've shown that it's really done a great job at helping plants and trees and larger plantings get their rootings. So here, I'll just play it. So you can see him scooping down into that soil, and then I'll lift it up and just let it drop. So it doesn't have to be fancy, it doesn't have to be careful. You're really just trying to diffusely mix in that rich compost into that very, very dense urban soil below it. So here he goes again. He's going to scoop it and just dump it. So it can be done pretty quickly. Let me stop this. And I'll go back to my PowerPoint. See, I'm learning things too. Got to learn all sorts of new things during this pandemic.
Boy. All right. Very good.
I think I've got just 1 or 2 more. So leaf cycle, compost top dressing, tillage, urban soil rebuilding. And I did want to talk very briefly about some of the very specific things that you'll see urban localities do to help street trees get up and running. So this isn't stuff that you would really do on your own property. This is something that more like the county government or city government might do. Street trees are almost universally liked, but it's very hard for a tree to grow in that little pit of soil between the sidewalk and the roadway. So there's something called structural soil, which is something that quite a few localities are using. It's sort of a compromise between urban needs and plant root needs. What are the urban needs? You need to have a lot of ability to hold weight. If you've got a sidewalk running over the top, you can't have that sidewalk sinking down. If you have a roadway running over the top of this tree pit, you can't have that roadway settling down either. So structural soil is basically a mix of angular stone particles and nice organic rich soil mixed in between. And the stone particles basically provide the strength, the loading. So when weight is applied to the top of the structural soil, the stone particles sort of lock together, and they provide the load bearing that's needed for the urban needs. But there's big pore spaces full of rich soil, and that provides the rooting medium for the soil. So this is actually a new street tree with some urban structural soil planted behind it. It kind of looks like new paving, but that's actually the structural soil there. They haven't come and put the cement concrete walkway on top of it just yet, but that's what it looks like. It kind of just looks like organic enriched gravel, if you will. But that swath of structural soil will allow the roots to pass through what otherwise may have been an impenetrable barrier represented by that sidewalk. And the roots now be able to pass through that and then access the looser soil in the lawn to the left. And hopefully that tree will be able to grow big and healthy. A little more intensely, we have something called tree box filters, and it's basically an underground vault for roofs. And it's got this lattice work of either metal or heavy plastic that, again, provides the urban need, which is load bearing, so traffic can drive across it. But it's got a lot of open void spaces, which allow the tree roots to pass through. So here's a tree box filter being installed next to a roadway, and you can kind of see that lattice work going in. So that's going to get covered up by paving, and you can park on top of these things. They really hold a lot of weight, but there's also all those open spaces that allows the tree to pass its roots through, which is good for both the tree, and it's also good for the surrounding paving as well too, because you probably won't see those root heaving that you see a lot in sidewalks around here. You know, the issue with this is obviously this is a pretty expensive project. You can imagine how much it would cost to dig out that much concrete, dig down into that compacted soil, and apply all of these fairly high-priced materials. So it's expensive, but they do work. They really can give your urban street trees a real boost. There's also something called flexible paving, which you can see in parts of Arlington. You see a lot of it in DC. If you're walking down the street and all of a sudden you hit a section of regular asphalt-looking sidewalk that feels very soft underfoot, sort of rubbery, that's flexible paving, and it is kind of a rubbery type material. They use similar types of material to surface playgrounds and tracks in some places as well too. And it's just a flexible rubbery type of paving which you can walk across, but allows tree roots to grow under, and it will heave, it won't crack as the tree roots grow underneath it. So it can have a benefit for the municipality too, in that they don't have to keep coming back and fixing the paving to get rid of those cracks and tripping hazards. So getting to the end, if you're curious about the type of soil that you have on your property in either Alexandria or in Arlington, my first stop would be to go to the soil survey, which is basically a map and descriptive tables of all the soil within those jurisdictions. For either Alexandria or Arlington, you can go to the Web Soil Survey. It's a pretty long URL, but there's only one Web Soil Survey, so you can just go into Google or Bing and search for Web Soil Survey, and this will pop up. And you can look up any other soil maps from any other area in the US as well too, since it's a US Department of Agriculture website. Specifically for Arlington County, Arlington County's got a great GIS website at maps.arlingtonva.us, and you can look up the soil maps just for Arlington County there, as well as many other interesting maps as well too. I'm sure Alexandria has a GIS website too. I'm just not as familiar with it, and I don't know whether they have the soil survey up there or not. But if you're curious about your soil, those are the two websites I would go to. And this is just a screenshot of the soil survey from South Arlington along 4 Mile Run Drive, just to give you an idea of what the soil maps look like. That's it for me. If any of you have questions now, of course, I'll stick around and answer them as best I can. Or if a question pops up in the near future, feel free to give me a call or shoot me an email, and I'll do my best to answer it as well too. But Nora, I'll throw it back to you and see if there's any questions that came in.
Well, thank you so much. And yes, there are questions.
Great.
I guess the very first one has to do with that soil map.
Mm-hmm.
How how useful is that if, like, you're on a street like I am, where my my lot hasn't been built on in 50 years, but across the street from me, there was a huge new development, and they, you know, scraped all the earth off and moved things around. And how useful is that map, looking at all the changes that have happened?
The caveat I always give with soil surveys is that they are for general planning purposes. So it's not going to be a site-specific map. I would say it's more useful for a property like yours where nothing has happened in the last 50 years. And it's going to be significantly less useful for that new development across the street. But you'll see that in the maps, they did try to compensate for that as best they could by creating a lot of what are called soil complexes. So you'll see a lot of soils that say Wheaton Urban Land Complex or Glenelg Urban Land Complex. The more developed an area is, the harder it is to describe the soil because so much changes during the development. But it has some use, but it's not going to give you a highly detailed, highly site-specific description of your soil type. It's going to be fairly general. So I'd say look at it, but certainly if you're trying to figure out what to grow, you can start with the soil survey, and that'll tell you some basic things like what kind of drainage you can expect, where you can expect the water table, where you can expect the bedrock to be, big things like that. But if you're looking at more specific things like the pH, the nutrient content, you have to get a soils test in order to do that, because the soil survey just won't be able to give you that kind of detail.
Okay. And by the way, folks, my electricity just flickered and there's thunder outside. So if we go off the air, thank you so much, Dan.
You're welcome.
But so there was a question from Dean about, I have a large number of mushrooms coming up in a shaded corner of my yard. Is that good, bad, or neither?
I don't think it would be bad. It probably means there's some tasty decomposing material somewhere down there. Oftentimes you can find it in sort of wetter areas of the soil as well too. But mushrooms are decomposers, so they're breaking down something. Maybe you have some harder to decompose stuff down below. Maybe there's some woody debris or something, maybe an old tree stump or something like that, or an old dead root buried down below that those fungi may be breaking down. Fungi, generally speaking, are better at breaking down woody debris. So you find a lot of fungi in forest floor areas. The soils under forests are generally more dominated by fungi than bacteria. Bacteria are better at breaking down the easy to decompose stuff, the starchy materials, the sugary materials, stuff like that. But I don't think there's any problem with you having fungi in your yard, and they're breaking down something, so they could be releasing some good nutrients at the same time.
Okay, and Noreen wants to know, why don't we have deeper topsoil in Virginia, like Nebraska,
Good question. We generally tend to find that areas that are naturally grassland or prairie have really deep topsoil. Our soils and the vegetation we grow here, a lot of the mass is above ground. You think about a big oak tree, that's a lot of above ground mass. And it's got a lot of below ground mass too. It's got a very big root system as well too. With grasses, they're not that big above ground. Some grasses can get pretty tall, 7 or 8 feet or so, but they have really deep, extensive root systems. The root system on a native prairie grassland is really incredible. It can go down 10, 12, 15 feet in some cases. And those big, deep root systems tend to pump out a lot of organic matter into the soil as well too. So former grasslands, or current grasslands, of course, generally tend to create soil that has a very nice, thick A horizon. So if you go out to Illinois or Iowa or Nebraska or Kansas or even parts of Texas and eastern Colorado, you can conceivably find soils that'll have 12 or 18 inches of topsoil. Whereas around here, because of the climate we have and the types of plants, trees that are sort of our dominant organisms, our climax organisms, they just don't build up that level of topsoil.
And a plug for leaving whole leaves for the insects if you can, because they can overwinter rather than chopping it up. But
I'd say definitely, you know, a lot of it's aesthetic, but whole leaves make a great mulch if you have got a planting bed or an area that is not open grass. Leaving the whole leaves on the grass could be an issue because you potentially could smother them. So that's why people a lot of times will chop them up on the grass. But certainly if you can rake it aside and use it as a mulch on your planting beds, on your mulch beds, that would be a great way to do it as well too. A great way to both leaf cycle and provide that cover habitat for the insects.
thank you. Okay, I noticed one of the soil tops in Arlington is PA loam. Are soils named for the first place that soil is found?
Yes. So locally, I don't think there's any Arlington loam or anything like that, but I know, well, for instance, one of the soils I mentioned before was Wheaton, and that's named after Wheaton, Maryland. There's a Fairfax loam, which of course is named for Fairfax County. There's Chantilly, there's Ashburn, there's a Dulles silt loam. So there's quite a few soils named after the local area. But yes, they're named generally after the town, city, locality where closest to where they were first described.
Okay. Do the organisms in the soil also help make nutrients available from the inorganic solids?
Yes, yes, they can. And actually, you can see this clear during the early stages of soil formation. So for instance, I helped teach a class for the master naturalists, both in Arlington and Fairfax. And with the Fairfax group, we always take them on a soil and geology field trip to Riverbend Park. And at Riverbend, they've got these great rock outcrops. And on the rock outcrops, you can see mosses and lichens forming. And those mosses and lichens put out natural acids, which break down the rock, the bedrock. And that's sort of the first step in soil formation right there. So there are ways that the microbes can break down, well, that wouldn't be a microbe, that's a macroscopic organism, but that living organisms can break down mineral material, yes.
Okay, and here's one. Does digging in soil create the bathtub effect? An arborist told us not to plant in the rain. She was right. The trees we planted died.
A lot of it depends on the soil type you have. If your soil is not too compact, if it drains pretty well, I wouldn't worry too much about that. I think it's still a good idea not to plant in the rain because you want the soil to be kind of loose. You know, I just think if you were planting in the rain, you can kind of cake and smear the soil on the inside of on the exterior of the hole that you dig. But you know, even if you're digging in really dry soil, if you've got really dense soil, and let's say you dig out a nice big bowl for your new plant and you plop the plant down in there with some loose planting soil or compost amended natural soil in there and water it, the water may quickly pass through that compost amended soil, but then it could hit that wall of dense soil that you had in your yard before and just sort of stick there. So it is possible to create that bathtub effect, yes. But a lot of that has to do with the quality of the soil to begin with. If your soil is fairly loose and porous, I wouldn't worry too much about it.
Yeah. Okay, well, that's it. Well, thank you so much, Dan. And like I said, in a day or so, I get a email from Zoom about where to find the recording, and then we'll share it with everyone. So you'll be on the internet, Dan, as if you're not already.
Well, thank you very much, Nora.
Okay, thanks so much, and everyone. I'll get you out information and get together with you August 4th for the what are we doing? Tree ID. So have a good night. Hope the storm doesn't hit.
Thank you.
Thank you so much. This was fascinating.
Yeah, we'll
I
see you
enjoyed it.
later.
Appreciate it.
Thank you.
Okay, bye.
Bye.
Bye-bye. Thanks, everyone.